So welcome to video 2 in our course ST4 on linear models. And in this part of the course, we're looking at correlation and covariance. So let's look at some terminology associated with this area first. Firstly, the expected value of x is effectively the mean value of all the values in x. It is the weighted mean value of all the values in x. So we weight the frequency of we've observed for that particular value of x. And the product of all of these adjusted for the sample size gives us the expected value. Note that the expected value, because it's just one single value, like the value 6, the expected value of the expected value is just one value as well. So that's the same, it's the same thing. We can also note that we're denoting R as the sample product moment correlation coefficient. Sometimes that's written in some resources as the capital R. And then we're talking about the regression of y on x. So we're trying to infer y based on the variance in x. We write this as y, the thing we're predicting, as a model A, the intercept, plus B, which is the slope, and A, that other variable. So we're assuming that there's some sort of monotonic relationship between x and y, so that it's the linear increasing, linear decreasing, maybe there's no correlation, but that the variance of x and y are independent from each other as well. So B is our estimate of the slope, which is the covariance of x and y together divided by the variance of x. And we can estimate A from this, from the mean in y, by B, the slope, by the mean of x. So we're able to estimate, maybe using least squares regression, the value for B and infer A from that. It's sometimes written as the Spearman's correlation coefficient, and that's used for ranks. So we write rho instead of R for ranks. And this simply is transformed the existing data sets of x and y into ranks and looks at the extent to which they're correlated, where the ranks are single integers for those data sets. So we can think of it that our pattern model is that if we write it like this, we have some sort of trend here, but we're thinking about the signal as going across our diagonal axis as a noise as being perpendicular to that. So the extent to which this noise is given by the height of each point compared to our line here. So if that height is going vertically, so we're going down here for this point, this line here, that is inferring our estimate y based on x. If we're going diagonally here across here to this point here, that's inferring x, and that's x hat based on data from y. So what we're looking at when we're looking at correlation is the tendency of two variables to covary. So we're looking at two variables, height and weight, and the extent to which they covary. So in our studio, what we might write is we might have a vector of heights and then also a vector of weights, and we could plot them to look at them first of all. And if we do that, then we can see, okay, they seem to have some sort of positive correlation, and maybe there's some sort of trend line, best fitting line, or best fit based on linear correlation that goes in between them, something like that. And then we can say, okay, that there's some sort of error there for our model. Maybe it's a decent fit, but we can take the sum of squares of these values to estimate how much error there's present. So we fit that best fit line like this, and to write that in R code, we write LM to denote a linear model, and we're estimating weight on the y-axis based on height on the x-axis. So that's why I write it as weight tilde height, and we've colored that in red. So LM is a linear model function. Avline draws a line based on input data from this argument. We can also estimate the correlation, which is 0.7 here. So you can see that height and weight are positively correlated. If we have different data, so we've changed weight here, we've changed height here, you can see that we have a negative correlation. Here's minus 0.9. So that's the correlation coefficient, and we take the square of that to get the extent to which the shared variance of x and y, which is 81% here. So for example, if we have heights and weights here, which have a mean of 2 plus minus 0.9, and weights have a mean of about 47 plus minus 14. If the R squared is 0.49, we can say 49% of the height variation explained by the variation weight, and vice versa. So to estimate that, we might have this as an example. So if we look at other terminology I might use, we say the expected value of x is 2.8, and the variance of x is 0.06 squared. So that means the standard deviation of x is 0.9. And it's the same for y. The expected value of y is the mean of y, and this is the variance of y, which is the standard deviation squared. We can then look at the expected value. We know that the variance of x is given by this equation, where it's put over n minus 1 by the sum of the squares. It's the same for the covariance of y, but here you note that we're doing xi minus x bar and yi minus y bar here. So the covariance of x and y together is like the variance of x and y. And we can show as well that the variance of y is equal to these terms. So we look at the product of the expected value of x minus its mean and y minus its mean. We get this at the end. And we can show that because we can expand this as having x and y, the expected values together here, x minus the expected value of y minus the expected value of x, and the product of the two expected values together. Now, if we simplify this, well, this is what we get at the end, because these two terms will cancel here. So that means when we're trying to work this out, we were effectively looking at the covariance of x and y together divided by the variance of x and variance of y divided by the square root. So r squared therefore is equal to the variance of x and y. So the variance of xy there, and that's we have in the denominator the variance of x, and then also the variance of y. So that's our formula. And when we put this into plots like this, we can see that we can have perfect negative correlations where, again, r is going to be at -1, which is given by this axis down here. We can have mild negative correlations, no correlation, a medium positive correlation, and a very strong perfect correlation as well. There's a nice illustration by Anscombe and what's called Anscombe's quartet, where we have deviations from our model. So we have our traditional correlation up here, where you see there's no underlying pattern between for x nor for x1 nor y1 across this line here. Whereas if we look at the other plots, we see that there are trends going on. There's other factors here. So you may have to transform x in this the x and y values here because there's some sort of curve going on. Similarly, for this, we see one data point is out of sync with what the other sequence is, and that biases our model. A model is not useful here because it doesn't really follow the pattern here. And the same for this one. We have x1, we have clear single values that's quite different from the others. So this is more of a categorical problem than one that to which we should apply correlation. All these have a correlation coefficient of 0.82. However, this is the only graph where it's appropriate to use that. In the same way, we've looked at the variance of y, and we'd prefer that their variances are not correlated with each other, so that their variance are consistent as the numbers increase. We might find that the variance increases as the value increase. So EI stands for our error. We might find that it increases and then decreases as well, or that we have some sort of correlation within that the values, the mean of the values decreases and then it increases as well at the end, and the variance maybe is stable around that, but actually a linear model is not appropriate in that case. We can also look at our data points and look at them very carefully here. So we have two groups, one in black, one in red. We can see that the correlation for each of them is slightly higher for the black group than the red group. We should note that we've got for the black group, we've got several values at the extremes here that might be cause of concern, because if one of these moved extensively, this correlation coefficient would vary a lot. Whereas for red, the correlation is lower overall, and we've certainly 1 or 2 extreme values here. But as interpreting these based on their p-values is not informative. We should be concentrating here at the effect sizes, which will tell us more about the underlying biology that's what's going on. So these groups are not really different, even if we have some arbitrary p-value threshold. The correlation coefficient is much more informative for each of these, telling us about the effect size that's going on. We can look at these other examples here where we have some sort of outlier that can skew our data. So here we've got an R of minus 1.414, but there might be more negative if that outlier wasn't present. We can have another example here where you have a small spurious correlation that makes positive from this outlier. You see that the distribution of data is the same. And then we have this one out here, which turns out to an R value of 0.54. And again, that illustrates the extent to which outliers can really affect our data. So consequently, when you're looking at correlations, if we have something like this where there's no underlying pattern, that's great. But we should be careful with instances where we've data that's categorical, needs to be transformed or assessed more carefully, has some sort of clear outlier, has multiple correlations going on, or maybe there's 2 different groups with a negative correlation that might be interpreted as positive correlation if we lump them up together. You can think of Simpson's paradox there. So that's the end of this video. Please see the next one on transforming correlation coefficients.